Scientists just drilled a hole through 2,000 feet of Antarctic ice, and what they found on the other side could rewrite the future of our planet. Right now, a single glacier the size of Great Britain is coming undone. It holds enough ice to raise global sea levels by 2 feet on its own, and it acts as a plug, holding back an entire section of the Antarctic ice sheet with enough water to raise sea levels by 10 more. For decades, we believed its collapse would take centuries, a distant problem for a distant generation. But new data shows the process is accelerating in ways no model had ever predicted. The critical point of no return isn't 100 years away. It may not even be a decade away. The failure has already begun. Not a minor fracture, not a seasonal melt, a structural disintegration. So an international team of researchers launched the most ambitious, most expensive polar expedition in human history. They sailed to the end of the Earth to get a first-hand look at the world's most dangerous glacier. But the readings they got back were worse than their darkest projections. The question is no longer if it will collapse. The question is how fast. And did humanity just receive its final warning, or has the doomsday clock already run out? The Thwaites Glacier was never supposed to matter this much. It sits in West Antarctica, a remote, brutal, and almost impossibly inaccessible part of the continent. The region is governed by the Amundsen Sea, an embayment of the Southern Ocean perpetually choked with sea ice, guarded by weather systems that can ground flights and trap ships for weeks. Temperatures here rarely rise above freezing. The winds are constant. The isolation is absolute. By any reasonable measure, this place is hostile to human life, a fortress of ice at the bottom of the world. And yet, the fate of coastal cities from Miami to Mumbai may be decided right here. For most of the 20th century, Thwaites was just a name on a map, a colossal river of ice nearly 80 miles wide flowing into the sea. It was named in 1967 after a glacial geologist named Frederick T. Thwaites, a man who never even saw it. To the scientific community, it was big, it was slow, and it was stable. The real focus was on Greenland, which was melting faster, and on the Antarctic Peninsula, which was warming more rapidly. Thwaites was considered a sleeping giant, a problem perhaps for the 23rd century. That assumption was built on an incomplete picture, a picture drawn before we had satellites that could measure the changing thickness of ice from space, before we had underwater robots that could map the sea floor beneath a glacier, before we understood the terrifying geometry hidden under the ice sheet. That old understanding began to crack in the 1990s. Satellite radar interferometry, a technology that allows scientists to track the movement of ice with millimeter precision, started sending back disturbing data. Thwaites was not stable. It was accelerating. The river of ice was flowing faster into the ocean year after year. The numbers were small at first, a few percentage points of increase, but the trend was undeniable, and it was persistent. By the early 2000s, Thwaites was responsible for approximately 4% of all global sea level rise. One single glacier. That number got everyone's attention. The sleeping giant was waking up, and scientists realized they knew almost nothing about what was stirring it. The problem with Thwaites is not on its surface, it's what lies beneath. Most of the West Antarctic ice sheet rests on a bed of rock that is below sea level, and crucially, that bedrock slopes downward as you move inland. Imagine a massive block of ice resting on a ramp that gets deeper the further back it goes. This is what geologists call a retrograde slope. It is a geometry perfectly designed for catastrophic failure. As long as the glacier's edge, its grounding line, is pinned on a high spot, a ridge on the seabed, it remains relatively stable. But if it retreats off that ridge and onto the downward slope, a vicious cycle begins. The warmer ocean water can now attack a taller cliff face of ice. The melting accelerates. This causes the glacier to retreat even faster, exposing an even taller, more vulnerable ice front. It is a runaway feedback loop, a planetary-scale demolition that once started may have no natural stopping point. Thwaites Glacier, the widest glacier on Earth, sits squarely on top of one of these retrograde slopes, and its grounding line is in retreat. For decades, the only thing holding Thwaites back was its ice shelf, a vast floating extension of the glacier that juts out into the Amundsen Sea. This shelf acts like a cork in a bottle, or more accurately, a buttress on a cathedral, providing a crucial braking force that slows the flow of the grounded ice behind it. It is the single most important feature preventing a runaway collapse. That ice shelf is now shattering. In the year 2000, satellite images revealed a massive network of fractures spreading across its surface. By 2014, scientists were tracking a chasm growing at a rate of 2.5 miles per year. Then, In late 2021, new research confirmed the entire eastern ice shelf, a section the size of a small country, was likely to disintegrate within 5 to 10 years. The buttress was failing, the cork was coming out of the bottle, and the consequences could be measured in feet, not inches, of global sea level rise. The numbers are difficult to comprehend. Thwaites Glacier itself contains enough ice to raise the oceans by approximately 2 feet. That alone would be a global catastrophe. It would redraw coastlines, displace hundreds of millions of people, and inundate infrastructure that took a century to build. But Thwaites is not just a glacier, it is a keystone. It stabilizes the glaciers around it. If Thwaites goes, it could destabilize the entire West Antarctic ice sheet, a process that glaciologists refer to as sector-wide collapse. The full ice sheet holds enough frozen water to raise sea levels by over 10 feet, not a gradual rise, a potential surge over decades, a change so rapid that adaptation would be impossible. This is why Thwaites earned its nickname, the Doomsday Glacier, a single geographical feature with the power to initiate a planetary crisis. The scientific community was no longer dealing with a distant threat, they were facing an emergency. And they needed answers. Fast. The mission was unprecedented. In 2018, the US National Science Foundation and the UK's Natural Environment Research Council joined forces to launch the International Thwaites Glacier Collaboration, or ITGC. It was the largest and most ambitious joint research program ever undertaken in Antarctica. The price tag exceeded $50 million. The logistics were a nightmare. The goal was simple: get instruments and people to the grounding line of the Thwaites Glacier and figure out exactly what was happening underneath. To do that, they would need ice-breaking research vessels capable of navigating the world's most treacherous sea. They would need specialized hot water drills that could bore through half a mile of solid ice in sub-zero temperatures. And they would need robots, autonomous underwater vehicles, and AUVs designed to operate in total darkness under immense pressure in an environment no human has ever seen. One of those robots was named IceFin. It was developed by a team at Georgia Tech. IceFin is a narrow, torpedo-shaped submersible just under 13 feet long, packed with sensors, cameras, and sonar. It was designed to do one thing: be lowered through a borehole in the ice and swim out to the grounding zone. It was a probe sent to explore the glacier's weak spot. In early 2020, after days of effort, the ITGC team successfully drilled a borehole 2,300 feet deep, piercing the Thwaites ice shelf just a few miles from the grounding line. The pressure, the temperature, the sheer isolation of the effort were immense. They were working on a floating platform of ice, hundreds of miles from the nearest permanent research station, being entirely dependent on the equipment they had brought with them. There were no second chances. Slowly, they lowered IceFin into the narrow abyss. The robot descended through the ice into the dark ocean cavity beneath. For the first time, humanity had eyes on the underside of the Doomsday Glacier. What it saw was terrifying. The prevailing theory had been that the melting was a relatively uniform process, a slow, steady erosion of the ice shelf's base by ocean water that was just a fraction of a degree above freezing. The models were built on this assumption. The models were wrong. IceFin's cameras and sonar revealed a landscape unlike anything scientists had expected. The underside of the glacier was not smooth. It was a chaotic terrain of deep canyons, vast terraces, and jagged crevasses, all being carved out by flowing water. And the water was not just slightly above freezing. The sensors detected streams of ocean water more than 2 degrees Celsius above the freezing point, flowing directly into the grounding zone. These weren't gentle currents. These were rivers of relatively warm, salty ocean water being funneled directly to the glacier's most vulnerable point. The water was attacking the ice not as a slow solvent, but as a blowtorch. The rate of melting in these channels was orders of magnitude higher than the models had predicted. The glacier was being eaten from the inside out. The discovery fundamentally changed our understanding of the collapse. It was no longer a story of gradual, large-scale warming. It was a story of targeted, aggressive erosion. These channels and crevasses dramatically increase the surface area of the ice that's in contact with the warm water, accelerating the melting process exponentially. Even more alarming, the robot's sonar maps showed the grounding line itself was not retreating in a neat, predictable line. Instead, the warm water was getting deep into the glacier's base, melting it out in a complex pattern, causing pockets of the ice to lift off the seabed while other parts remained pinned. The glacier wasn't just sliding backward, it was being unzipped from the rock below. This chaotic retreat makes the glacier far more unstable and its future behavior far more difficult to predict. The steady, linear projections of the past were now useless. The system was behaving in a non-linear way. The collapse was feeding on itself. But the ITGC's findings didn't stop there. Another team working on the project used seismic sensors and radar to peer through the ice. They were mapping the bedrock beneath Thwaites, looking for anything that might slow its retreat. What they found was the opposite. Beneath the thickest part of the glacier, they discovered a network of deep sedimentary basins, essentially ancient river valleys carved into the rock. These basins are filled with soft, water-saturated sediment. This sediment layer acts like a lubricant. It reduces the friction between the glacier and the bedrock, allowing the ice to slide even faster once it comes ungrounded. It was another feedback loop that had never been included in the models. The glacier was resting on a foundation that was primed to help it fail. And every new piece of data gathered by the ITGC seemed to make the problem worse. The water was warmer than we thought. The erosion was more aggressive than we thought. The geology was more slippery than we thought. The picture was getting clearer, and it was a portrait of a system racing towards a tipping point. The most profound threat, the one that glaciologists are now wrestling with, is a theory called marine ice cliff instability, or MICI. It is a concept that moves the Thwaites problem from a crisis to a potential cataclysm. The theory is straightforward. Ice has a physical limit to how tall a vertical cliff it can support before it shatters under its own weight. That limit is estimated to be around 100 meters or 330 feet above the waterline. As Thwaites retreats down its retrograde slope, the height of its ice front exposed to the ocean will get taller and taller. Once it passes that 100-meter threshold, the cliff face could begin to collapse catastrophically. Great walls of ice would calve directly into the ocean, not because they melted, but because they simply broke. This collapse would expose a new, even taller cliff face right behind it, which would then also collapse. It would be a chain reaction of structural failure, propagating backward into the heart of the ice sheet at a rate far faster than any melting process. MICI is the doomsday mechanism, a rapid, unstoppable disintegration. The debate among scientists is no longer about whether MICI is possible. The debate is about whether it has already started. Some of the fracturing and calving now being observed at the glacier's edge looks disturbingly similar to what the MICI models predict. The $50 million mission to Thwaites was a monumental feat of scientific engineering. It delivered a torrent of data that has transformed our understanding of cryosphere dynamics. It gave us the clearest picture we have ever had of our planet's most immediate climate threat. And yet, the result of all that effort, all that investment, all that human ingenuity was to confirm our worst fears. The solutions are not as easy as drilling a deeper tunnel or conserving more water. How do you stop warm ocean currents from reaching the base of a continent? How do you repin a glacier the size of a country onto its bedrock? Some proposals have been floated, ideas bordering on science fiction. Geoengineering projects to build an underwater wall in front of the glacier or to pump colder water into the subterranean cavity to refreeze its base. The scale is almost incomprehensible. The cost would make any infrastructure project in human history look trivial, and the risk of unintended consequences is enormous. We are not engineers dealing with a faulty dam. We are observers of a planetary process that we have set in motion but no longer control. The winter of 2023 brought record-low sea ice extent around Antarctica. The oceanic buffer that helps protect the ice shelves from warm ocean waves was smaller than at any point in the satellite record. It was another stark reminder that the insulating systems of the past are breaking down. Scientists warned that this was not a one-off event. It was a sign of a new state for the Southern Ocean, a permanent shift. One good snow year in the Rockies can raise Lake Mead by 20 feet, but there is no equivalent process that can refreeze an entire ocean or regrow a shattered ice shelf. The changes happening in the Amundsen Sea are accumulating. They are not cyclical, they are directional, and Thwaites is not alone. Its neighboring glacier, Pine Island, is also thinning and accelerating, resting on a similar retrograde slope. Together, these two glaciers act as the arteries draining a vast basin of ice. The entire region is becoming unglued. What the ITGC has revealed is that the future of our coastlines is not a slow, gentle affair. It is a story of thresholds, of tipping points, and of collapses that happen not over millennia, but over the course of a single human lifetime. The data from Icefin wasn't a warning, it was a diagnosis. The disease is in the system, and it is progressing. The international Thwaites Glacier collaboration proved that we have the technology to understand our world in astonishing detail. We can send a robot to the seabed beneath a mile of ice at the end of the Earth. That capacity, that knowledge is remarkable. But it has also delivered an uncomfortable truth. Knowledge does not equal control. Understanding the mechanism of collapse does not grant us the power to stop it. The final reports from the ITGC are still being written, the data is still being analyzed, but the preliminary conclusions are inescapable. The Doomsday Glacier is not a future problem. It is a present-day crisis. The changes are happening now. The acceleration is measurable. The feedback loops are engaged. The hard limit that matters, the final point of no return for West Antarctica, may not be a temperature threshold we cross in the future. It might be a physical point on the seabed that the Thwaites Glacier has already passed. The ice still flows. The shelf still stands for now. But deep beneath the surface, in the total darkness under 2,000 feet of ice, a clock is running. And it is running much faster than we ever thought possible.